In this short lecture, we will introduce interactions and marginal effects. It may seem complicated at first, but I assure you, once you wrap your mind around them, they're not that hard. So what do we mean by marginal effects? A marginal effect is essentially what we've been talking about. It's the effect of x on y, but we call it a marginal effect when there's something a little bit more complicated than just a single variable model. And the way we figure out a marginal effect is oftentimes by taking the derivative of the regression model with respect to the variable that we're interested in this case, x. So these little d's, these things here are partial derivatives. You probably haven't seen them before, but it's essentially the same as taking a full derivative like dy dx, except we're now doing it with respect to only one variable, so we technically need to call it a partial derivative. So let's do an example here with a single variable model. The marginal effect of x on y is just going to be the derivative of this function here with respect to x, which is dy over dx, and that gives us beta 1. So it's just getting us the slope, or the effect of x on y. Suppose our model has two variables, x1 and x2. The marginal effect is going to be the derivative of this function. Well, technically the partial derivative of this function with respect to x1. And so the marginal effect of x1 is going to be beta 1 here. And the marginal effect of x2 is going to be beta 2. And so this kind of gives you a sense of why we have to use partial derivatives, because sometimes we're going to be taking the derivative with respect to one variable, and other times we'll be taking it with respect to other variables, holding each of the others constant. Now suppose our model, and this is what we're introducing today, suppose our model has an interaction, x1 times x2. So the marginal effect of x1 is then going to be beta 1 plus beta 3 times x2, because that's the derivative of this function. When you take the derivative with respect to a variable x1, it's going to fall out and then be multiplied by what's left over, beta 3 times x2. Likewise, the marginal effect of x2 is beta 2 plus beta 3 times x1. Okay, suppose you want to find out how female, let's do some examples. You want to find out how female and education affect earnings on average, or being female and education levels affect earnings on average. So you regress log earnings, y equals log earnings, on two binary variables. The first is, we'll call d1, and it's equal to 1 if the person graduated from college. And it would be equal to 0 if the person had not graduated from college. D2 will say is equal to 1 if a person is female, and 0 if a person is male, or otherwise. Regression is then going to be yi equals beta 0 plus beta 1 times the first dummy plus beta 2 times the second dummy. The problem is the effect of having a college degree holding gender constant is the same for males and females. According to this model, the effect of having a college degree, this variable here, is the same for males and females. And we might think that it actually differs for males and females. The value of having a college degree might be different for men versus women. So the solution to this problem, if we think this is the case, then we would just add an interaction term. We're going to multiply the two variables together. So this is literally, if you have your spreadsheet in Excel or your spreadsheet in R, you have one column that's D1 and one column that's D2. And suppose you have one value here and then another value here. These are your values in the rows, right? Then you have a third column that you create that's just d1 times d2. In this case, we have 1 times 0, so it's 0. 0 times 1, so it's 0. And 1 times 1, so it's 1. That's literally all we're doing. And then we add this additional variable to the model. So how do we figure out the effect of a college degree changing d1 equals 0 to d1 equal 1 on earnings? So if in this case we can't compute a partial derivative because you can't take a derivative with respect to a variable that's non-continuous like these dummy variables. So we compute the conditional expectation of yi for d1 equals 0 given a value of d2 as follows. So we'll take the expected value of our regression model of our dependent variable conditional on the independent variables taking on certain values. Specifically, d1 takes on the value of 0 and d2 takes on the value of d2. So d2 is going to be anything, any value 0 or 1. So the result is we get beta 0 plus beta 1 times 0 plus beta 2 times d2 plus beta 3 times 0 times d2. So the values that are multiplied by 0 are going to drop out, and we're just going to be left with beta 0 plus beta 2 times d2. And we use the conditional mean assumption that the errors are mean 0. And then let's compute the conditional expectation for d1 equals 1 given a value of d2. So the same thing here, the expected value of y given d1 equals 1 and d2 equals some value of d2 either 0 or 1. And so we get the results. We're just plugging in the values into the regression function. We get the following result, which is equal to this bit here, which is a little bit longer than what we found when d1 equals 0. And so the effect of a change, or the marginal effect in college status, is the difference between the two. So we can just subtract these two, and we get beta 1 plus beta 3 times d2. So we're subtracting this value here from what we had there. And so that's going to get us the marginal effect the effect of a change in college status on earnings when we have an interaction. So how do we interpret this? The effect of acquiring a college degree, a unit change in D1, depends on the person's gender, the value of D2. How do we know this? Let's go back real quick. So the effect of changing D1 in our model, it's not limited to just a change in the gender. Now we have an interaction term, and so that the effect of the college degree is also included when we change the gender. So this means the effect of acquiring a college degree, the unit change in D1, depends on the person's gender, the value of D2. If the person is male, the effect of college is beta 1. So let's go back. If the person is male, the effect of college is beta 1. That's this bit here. And then if the person is female, D2 equals 1. The effect of college is beta 1 plus beta 3. And beta 3 is therefore the difference in the effect of acquiring a college degree for men versus women on earnings. So this says if you think that maybe women earn less than men on average, and that if somebody wants to earn more, they might go to college, that the effect of going to college is not going to increase earnings as much for women than it would for men. So beta 3 would be negative. This is compared to a no interaction model where the effect of acquiring a college degree is considered the same for men and women. Okay, let's do an example of an interaction between a continuous and dummy variable. So now we have y is again log earnings, x is the individual's work experience, a continuous variable in years, and d is again a dummy variable for attending college. So 0 you didn't attend college, 1 you did. Beta 2 is then the difference between the intercepts of the two possible regression lines, one for college grads and one for non-college grads, and we'll show an example of this in a moment. So we have an intercept for non-college grads when d is equal to 0, and an intercept plus another value here, beta 2, when d is equal to 1. Okay, so there's limitations to the model on the previous slide. Suppose we want the effect of an additional experience to differ for college versus non-college grads. So the solution, of course, is going to be an interaction model. We're going to multiply x times d, and this will allow for different intercepts and slopes of the regression lines depending on whether we are looking at college or non-college grads. The interpretation is, let's take the expected values again. Expected value of earnings, conditional on di equals 0 for x taking on any value x, and then the expected value of earnings, conditional on di equals 1 for any value of x. And when we plug those values into the model, we get, for di equals 0, we get beta 0 plus beta 1x, and for di equals 1, we get the additional intercept here, beta 2, plus the change in slope, beta 3. And notice how not only did the intercept change, but the slope changes as well. So we have, we could put maybe a parentheses around there, and we can see that this is the change. I'll use triangle for change in intercept, and this is the change in slope. Beta 3 is the additional slope for a college degree, and beta 1 is the additional, beta 2 is the additional intercept for a college degree. The difference between the slopes for college versus non-college grads is beta 3, and that is the difference in the effect of an additional year of experience on earnings, so we already said that. We already kind of covered most of the rest of this slide. Another version, we could also restrict the model to indicate that the slopes are different but the intercepts are the same. How would we do that? We would just leave di out of the model except in the intercept, or except in the interaction. So we used to have it as beta 0 plus beta 1x plus beta 2, I should put i's there, di plus the interaction. But now we're going to leave this part out, and that means that the intercepts are going to be the same by construction. So we have the model without the intercepts here. We take the expected values again for di equals 0 and di equals 1. We get, for di equals 0, beta 0 plus beta 1x. And for di equals 1, we get beta 0 plus beta 1 plus beta 2x. So notice how the intercepts are the same in both models. And this would be useful if we thought that the population entry-level wage was the same for college grads and non-college grads when experience equals 0. So what do I mean by this? Experience, wage. We're saying that when experience is 0, the effect of experience is exactly the same. So it would look like that. All right. Let's take all of this and put it into graph form. So this first, the upper left-hand graph here is the model without any interaction terms. So this is y equals beta 0 plus beta 1x plus beta 2d. So x is graphed on the x-axis here in all of the graphs, and y is on the y-axis, of course. And so this is saying, all right, the slope is the same. We have no interaction term. So notice how these two lines are parallel, meaning that the slope is always beta 1 regardless of whether d is equal to 0 or 1. But the only what changes is the intercept. So when d is equal to 0, this term drops out, and we're just left with the lower line here. We're assuming that beta 2 is positive. And then when d is equal to 1, we're adding beta 2 to beta 0, and we get this line here. So we have an upward shift in our intercept, assuming beta 2 is positive, but the slopes remain the same. And then these values, or these expressions here, are the regression lines when d is equal to 0 for this one, and when d is equal to 1 for this one. The next graph over to the right, we have different intercepts and different slopes. So our model is we have x included linearly, d included linearly, and the interaction of the two. So what happens when d is equal to 0? The beta 2 times d drops out, and the beta 3 times xd drops out, and so we're just left with beta 0 plus beta 1x. So that's the bottom line here, and our intercept would just be beta 0. So they've graphed that for us there. The slope is just beta 1, And so this is our regression line when d is equal to 0. When d is equal to 1, the beta 2 stays in the model. The beta 3 also stays in the model multiplied by x. And so we get a difference in intercepts, beta 0 plus beta 2. That's what they're giving us here. And we also get a difference in slopes because beta 3 is multiplied by x times 1. So we can simplify that by taking beta 1 times x. So what am I doing here? So let me make that a little more explicit. I'm going beta 0 plus beta 1 x plus beta 2 times 1 plus beta 3 times x times 1. And so we can take the beta 3 times x times 1 and add it to the beta 1 times x. And that's going to give us, let's do this, beta 0 plus beta 2. I'm just moving that beta 2 over. And then that's our intercept. Then we'll get beta 1 plus beta 3 times x. And that's what they're giving us here for the upper regression line where the slope is beta 1 plus beta 3. So with this interaction term, we're getting a difference in slopes and a difference in slope and a difference in intercepts. Okay, so the bottom one, this is where we're limiting the intercept to be the same for both conditions for D, but we're allowing the slopes to change. And so this is our model here for this graph on the left. D does not enter the model by itself. It only enters through the interaction. So if D is equal to 0, we get beta 0 plus beta 1x. That's what they're giving us for the bottom line, where the slope is equal to beta 1. But if D is equal to 1, then we still have the same intercept, but the slope is now beta 1 plus beta 2 times x, and that's what they're giving us for the upper regression line. So they're graphing these interactions for us, which is kind of nice. Okay, interactions between two continuous variables. Now suppose both independent variables are continuous. X1 is experience and X2 is years of education. And we can just create an interactive model where we have X1 times X2, just like we had X1 times D, but now we're multiplying by another continuous variable. And now the effect of a change in experience or education depends on the level of the other, just like before. In the non-interactive model, the effect of one variable does not depend on the outcome of the other. The interpretation is basically the same. To find the marginal effect of x1, take the derivative with respect to x1. And so if we do that, our model was y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 times x2 plus an error term. The derivative of this is with respect to x1 is just going to be beta 1 plus beta 3 times x2. This means that the effect of earnings on an additional year of experience, the effect on earnings of an additional year of experience is greater by the amount beta 3 for each additional year of education. So x2 is education. This means that the effect of earnings, x1, on, or the effect of experience on earnings, y, depends on the level of education, x2. And vice versa. The effect of x2 on y depends on the level of x1.